for our Saturday show. We're so glad you decided to come to Rutgers for Rutgers Day and spend some time here in the physics department. My name is Dave Maiulo, and I run this facility. I'm a very lucky person in that I've been doing this for 40 years. I basically get paid to play with toys all day long, and this is the result of that. But I'm really lucky. You see these wonderful young people that were out there showing all those demonstrations. They're the reason I actually still get up and have some hope for everything. You know, working with them really gives me a lot of hope. Just two things, housekeeping. One is a lot of people would like to know how to actually contact us after the show. There's sheets out there on that table, basically have our emails on them, plus a list of the demos you can access if you want to actually do that, and there's suggestions on that website about what you can do at home too if you wanted to try some of these things. Not all of them you can do at home too. And everybody should have a pair of these. So if you don't have a pair of these, make sure that you get one because you're going to need those for later on in the show. Don't tear it in little pieces before you get to them either. You'll have to use them. Without further ado, Mark.
Well, I'm Mark Croft. I'm now a professor emeritus here at Rutgers. And basically, we do this show to watch all the kids have fun with physics and science and learning. And so we're going to run it like a physics course, except today it's really charged. It won't be too boring. And so we start off with Newton's laws. And the first of Newton's laws that you'll notice that Dave guides me around quite often. The first of Newton's laws is objects at rest tend to stay at rest, and objects in motion tend to stay in motion.
Let's make it more dangerous by lighting the candle.
There you go.
You know, there's actually romance in physics too. Here it is.
So we're going to discuss the friction here. But now these objects are at rest, and if I pull this guy fast enough, the friction won't take over, and they'll remain at rest. And so the object at rest remain at rest. I hope I won't lose my glasses.
Yes.
The second part of that is that objects in motion tend to stay in motion. And actually, we would have been a lot further along if Aristotle had played ice hockey. Because in ice hockey, you hit it once and it goes on practically at constant speed for a long, long distance. But he didn't play ice hockey. So he said if an object is put into motion, it goes to its state that it likes to, rest. Just like me sleeping on the couch at home with Miss George. And so, but Aristotle didn't know that. He didn't have a ice hockey or an air puck. So an object in motion tends to stay in motion at constant speed in a straight line.
Oh, another force, right?
Until another force acts upon it. But actually, they didn't even talk about forces at that juncture. Now we'll talk about forces. This one's force equals mass times acceleration. In other words, if you have a push that you do on something, how fast it changes its constant motion, that is no motion at all, into some speed, depends on how massive it is or how heavy it is. And so here is a light object. You hit it, it goes shooting off there. Let's move this back so we don't hit any of the audience. This one's a little bit heavier, and I put the same force on him. You'll be safe with this one. This guy's a lead brick. And so I can beat up all day, and he hardly changes his motion. Friction comes in there too. As a matter of fact, I can even put my hand under it and then beat on my hand. That doesn't hurt at all. Okay. Our gritty fingers don't go over well with that. Now there's another thing. We're going to do force reaction force in a second, but here is an example of two objects interacting, and they'll have a forcing. They're called these buzz magnets. And the neat thing, and this is where Newton got some of the ideas for gravity, action at a distance is incredibly important. All the stuff I've shown you had something hitting or pushing directly on something. But this one just sits there guy goes by. Oh, that's all right, let him go. This guy goes by, and the two snap together. So they start pulling to each other before they even touch each other. Action at a distance. He got it from magnets and Sir Humphrey Gilbert, and then Newton used it for gravity.
That's right. We're going to see now another example of Newton's second law for every action. Force equals mass times acceleration. And what are we going to do to actually use that as a demonstration? Well, we're going to use the force of our atmosphere as the actual force to push something. So what we have here is this long tube. On one side we have a ping pong ball inside here, and this tube is connected right here to a vacuum pump. We're actually going to go ahead and pull all the air out of this long tube by pulling on the vacuum pump. Now remember, the atmosphere is over us all the time, and it's pressing down on us all the time. You really don't know how much force is pressing down on you because you're always in it. You ask a fish, hey fish, how's the water? The fish is like, what are you talking about? Because they're always in it. I ask you, how much force is pressing down on you? Yeah, I don't know, because you're always in it. Unless you're an astronaut, you're in climbed Everest. So that's what we're going to show you, is just how much force the atmosphere has. But remember, Newton's second law is force is equal to mass times acceleration. So, inside there is that ping pong ball, sitting right inside there. What I have here is a very sharp blade. I'm going to take this sharp blade, and now that all the air is out of this tube, I'm going to pop that side. When I do this, the same force of air that's pressing down on all of you is now going to press on that ping pong ball. Force is equal to mass times acceleration. The ping pong ball will accelerate down the tube. And when it leaves this side of the tube, it will be going 700 miles an hour. Yeah, that's faster than they drive on 287. So, let's see just what this can do to what's over there. 3 cans, 3 soda cans. They're empty, but they are made of metal. But let's see what a ping pong ball can do to metal soda cans when it's pushed by our atmosphere. 3, 2, 1. What did we do? What did we do? Did anybody actually see the ball move through the tube? No! Right? 700 miles an hour is pretty darn fast. But this is soda can number 1. Pop through with a ping pong ball by being pushed by our atmosphere. That force. Here's soda can number 2. Pop through with a ping pong ball. And these ginger beer cans are really strong, so it doesn't really go right. But there you go, okay? That's force is equal to mass times acceleration. Now we're going to do the third law. And Newton's third law is for every action, we have an equal and opposite reaction. What is that? Is that Mark? Nobody's talking.
Force reaction, sorry,
That's okay.
it was, the sound was too loud.
That's all. That's
Oh,
all.
yeah, it's cool, you were going to do this one.
I'm gonna do it.
Reaction force, so every force is an equal and opposite reaction.
That's the one, Mark. That's the one. So we're going to use this pretty red card to do this demonstration. Here's a nice example of for every action there's an equal and opposite reaction. I can take my body, I can press really hard on the surface of this cart. But the cart pushes equally back on me, holding me up. I push down, it pushes up. But there's no motion in that, right? Nothing was moving when I was doing that. But this law actually does give us motion. So, what's that in my hand? Balloon, thank you. What is it now? A popping balloon. No, a balloon filled with air. And if you take this balloon and let it go, what does the balloon do? It moves, but the air is going one way. What's the balloon doing? It's going the other way. Equal and opposite reaction. That's why this moves through the air. 3, 2, 1, and off it goes. But that's not so exciting. Let's try the exact same thing with this. What's this? A fire extinguisher filled with lots and lots of force. This fire extinguisher has all kinds of pressure in it, CO2 under all kinds of pressure. And I'm going to take all the force in that fire extinguisher and I'm going to hit that sail with all that force. Now, all you scientists, what I want you to do is tell me, when I do this demonstration, what direction does the cart move in? Use your hands. Which way does it go? I tell you what, I see hands going everywhere. Let's do a physics survey. Okay? Who says I go that way? Okay, good. Who says I go that way? Excellent. Who says I'm headed this way? Probably never. Who says I'm going that way? Sooner or later, not today, I hope. By the way, this is an extremely loud noise, so especially for you here right in the front, you may actually want to cover your ears. And it's just like a grenade, you can pull the pin. So, let's see which way I go. 3, 2, 1. Which way did I go? Nowhere. The only thing that happens is your butt gets really cold. It goes right down your shorts. But why not? You saw how much force I used on this, but there's no actual motion. Again, I'm pressing on myself. You press on yourself, you don't get any motion at all. What does Mark have to do to merely make this a rocket cart? Take the sail off. He's now going to take the sail off.
We're going to move back.
Oh, yeah. We're now going to back up.
Really where I at?
Yeah, right there. You're good. Just don't blow everything off that table.
Yeah.
Now I want you to see my motion. Which way am I going? It's obvious which way a rocket goes, right? You see a rocket, it's headed right that way. But I want you to see the amount of force that's on Mark 2. Because it's equal and opposite, which means he's going to get pushed around. 3, 2, 1.
Okay, now.
Oh, yeah.
Now, I originally invented that back before we had the card. And this is the way I used to do it. Let me see if I can make it a little larger. Doesn't have to be too large. There's a 50-pound fire extinguisher, and there I am on racing skates. And so I hold it so it pushes on my center of mass, but I don't have glasses insurance, and so I have to take my glasses. And then I take some time to work up my courage. I don't do that anymore. However, you noticed I bent over in a very strange way. It's not because I'm strange, it's not because necessarily I'm not strange either, but I was trying to make sure it pushed on my center of mass, because when I first did this experiment, I held it off center like this, and it puts me into rotation. And the way I discovered that was I did this first demo on the Rutgers floor in the math center, and I tried it. Nothing happened with a little fire extinguisher. I got so ticked off. I came back with a 50-pound fire extinguisher and a new pair of racing skates. And then at the low point of my common sense career in my entire life, I looked at the room floor and I looked at the nice smooth table and I got up on the table. I blew myself rotating and translating off the table. I only did that demo once. Okay, we're on this one? Okay, so now we'll do not motion in a straight line, but motion in a circle. And the nice thing I like about this is because the only thing you can do with a rope really efficiently is to pull. So if I exert a force on that, it's always a straight line to my hand. Pull it up, it moves up. And so when I swing this in a circle, I do a little wiggling of my hand to keep it going because of friction, but ignore that. Basically, all the force is pointing towards the center of the circle. And that's what keeps it moving in the circle. This works with satellites, or it works with balls on a string. And so if I let go of it, it resumes the no force natural motion, which is a constant velocity in a straight line, the Goliath effect. Or rather, the David effect. Goliath was on the other end of it. Now, the demonstrations that Dave lets me do still are usually the ones that endanger the professor, endanger the person, or make him look silly.
Or humiliate them.
Yes. And or get the people in the front row wet.
He's not good at this.
Yeah, that's also why maybe he makes me do it. Well, we'll see. Let's see if I can do the great waiters trade one more time. It's stopping that is the problem.
You may get sillier now.
Okay, what are we up to?
The lacrosse.
Oh, yes. So now we're going to talk about energy. Newton didn't have, he didn't formulate his laws in terms of energy. But there is a common sense, you know, everything seeks its lowest energy. So if you have something at a little height like that, and you drop it onto your toe, well, I missed the toe, but that's all right. It doesn't hit the ground with much speed or velocity. But if I hold it way over my head, it starts from a much higher height, more energy of position that can be converted into energy of motion, kinetic energy and potential energy. So it hits the ground much faster in the higher position. Now you can transform energy of position to energy of motion back and forth. Let me just give you a better idea of energy of motion. So I could really do it into this?
Oh, yeah.
I have your permission?
Yes.
Well, this just gives you, this gives you an idea of kinetic energy, low velocity. But high velocity, that's high velocity motion, and that's lots of kinetic energy. It's the difference between having somebody pitch you the ball and having a big leaguer pitch the ball. Okay, energy of motion, energy of position.
We're going to just talk about it, right? And then we'll set it up.
Okay,
You wanna show them
I can do it this way. Okay, we'll do the real thing. Here's a pendulum. The nice thing about pendulum is that you give it some energy of position and converts it to energy of motion at the bottom. So it goes back and forth. The energy of position where it turnaround points, it stops moving. Energy of motion when it's at the bottom. So position, motion, I can't say it fast enough. But anyway, it constantly converts it back and forth. And if it's a shorter pendulum, it converts back and forth faster. Okay, so there's a natural time. And here we have this idea of energy, conservation of energy. If you really believe something like this, you have to put your mouth where your money is, or your money where your mouth is.
The pendulum where your mouth is.
Yes. So I go way up here.
This is Rutgers' best ladder.
And it's from the 1932 football.
That's right. They have that.
And so if I started off here in my nose, well, I start at my chin. I know it's not going to come back and smash my chin because it will never go any higher than the amount of energy I gave it. So it converts the kinetic energy, and there you see a brick at the bottom. And I think about that brick. Now we're going to do the same thing. That shows you energy of motion converted into energy of destruction, and this is to prove that I really believe in conservation of energy. I don't have to worry at all.
Push that.
Unless I lean forward. Did I lean forward? I used to do demos where I would drop something from the ladder to prove how things fall, and I was going to trade on this one, then I would let go of it, fall off the ladder, and catch me on the way back. Okay, where we go? Okay, energy of
Now I'm
motion.
going to get you that.
And energy of position. I don't need a other things. A spring does the same thing. One stretch straight. But you can turn the force on spring and stretch it back and forth, right? It's a way of pulling your chest hairs out also. Okay, so if I stretch it, there's energy of position. I let go, it goes into energy of motion. And they go back and forth at a natural frequency, depending on the spring and the mass that is moving back and forth. Okay, so that's if you kick it, it always responds at that natural frequency. Now, often you don't just kick things, you wiggle them. So if I wiggle away from its natural frequency, not too much happens. Almost nothing happens, right? Really low frequency, almost nothing happens, right? The string doesn't stretch. But if I pull it at the natural frequency, the energy goes in at the same place every cycle. And the motion builds up, and up. That's enough. Now we're showing a few things that have to do with that.
Yeah, resonance comes in many forms, and kids, I'm about to give you a good example of resonance you can do when your parents take you out to a really, really, really good restaurant. Because these glasses are going to be on the table in front of you when you sit down in that restaurant. Now the waiter knows, the waitress knows you're too young to have any wine, so sooner or later the waiter's going to come wandering over and take that wine glass right from the table. Don't let that happen. Instead, you put the wine glass right there on the table. You hold it really tight right against the top of the table. You take your other fingers, you put them right there in your dad's water glass like that. And then you go ahead and just rub the top of the glass. You make that wine glass sing. Basically, you're getting a resonant frequency of the wine glass by putting your energy into the wine glass with your finger. So it gives you a nice, pretty sound. Well, what's the best part of this experiment in that restaurant? You're going to be bugging your parents. You knock it off. Bothering everybody in the restaurant saying, I'm doing physics, this is going to go on all night long. But who else is going to hear that sound? It is the waiter, right? The waiter goes, you can't do that in my restaurant. You know, this is a quiet restaurant. Say, waiter, I got a question for you. If I take the rest of my dad's water and I fill the wine glass, will it be a higher sound or a lower sound? He sounds just like the waiter. What do we have to do to find out? What do you do in life to find out? Do it. Do the experiment. That's how we really learn in life. And if you notice, it's actually a lower resonant frequency. You now have the density of the water, mixing with the density of the wine glass, gives you a lower resonant frequency. Just like that. So there you go. That's resonance in the wine glass. So we just showed you resonance with that wine glass, but right here inside here, we actually have a beaker. It's sitting inside our box, which is right over there. And what I'm going to do, I'm going to just blank a couple things out here. Let's see. I'm going to do that here. And good. I'm going to blank this, because we're going to need that ball. Good. And what I have in there is it's right next to a speaker, and since I can't touch it inside the box, I can touch it with sound. So that speaker is actually going to play a sound into the beaker. It's actually ringing the beaker. I know exactly the resonant frequency of the beaker. I found it before. So I can ring that beaker with the sound. Just like I'm touching it with my finger or the wine glass, but I don't actually have to touch it. I just have to play the resonant frequency into it. So it actually sings. But it's actually also moving quite violently. In fact, it's moving so much, I want to actually show you how much it's moving. And I can do that by taking the one light and turning it off, and turning on the strobe light. And now when I do this, you can see the walls of the beaker are actually shaking quite violently. But you scientists, what happens if I give it too much energy? Do you want to see that? Yes. And you're all good scientists. It's so close. No? All right. Well, we couldn't break that. You never know. I mean, sometimes they're in there, so you see how much violently it's shaking. Usually they do break, but hey, once in a while we make pyrites really good. There you go. Somebody, anybody. No one wants to volunteer? No one wants to be a scientist? Come on now. You could if you wanted to. Yeah, come on up. Come on up. Karini, so good to meet you. Thank you so much for joining us here for our Rutgers Day show. Karini, can you stand right over here? Okay, and then just face me, just like that. What I have right here is a long rope slinky. It's a long rope slinky. It's basically a spring. Karini, please put out 2 hands. I'm going to put that rope slinky there. You're going to hold on to it right there. You're going to hold it nice and tight. You're going to hold it right back there. Fantastic. Now, Karini, 3 things you have to do for us now, okay? Can you answer questions? So she's got that down already. She can answer a question. Number 2, can you be loud?
Yes.
Can she be loud? Yes. Okay, good. They know that too. Okay, good. And number 3, no matter what I do on the other side of the room, don't let go, because if you let go, I get hurt. No pressure. So, I'm on one side of the room with a long rope slinky. Karini's on the other side of the room with a long rope slinky. Let's check in with Karini right away. Karini, you feel a little force, a little pull right now.
Sure do.
Sure do, right? Of course, right? It's a spring. You pull on a spring, you feel the force. We know that. Now, Karini, don't move at all. I'll do all the motion. What kind of motion is that, everyone? Looks like a drum buck. Well, what do we call this in physics and in science?
Wave.
Wave. This is wave motion. It's a great big wave, but this is exactly what we have right here in a rope slinky now. Let's check it with Karini one more time. Karini, do you feel a little more energy and force when this is in motion?
Absolutely.
Absolutely. But do you notice this? The rope slinky's not moving towards Karini or away. It's just going up and down. She still feels all the energy of the motion. Because that's the true beauty of energy in waves. You know, nothing really has to travel with the wave but the energy. And that's exactly what she's feeling right now with this in motion, with this one singular wave. Now, Karini, just hold on tight. Again, don't move at all. I'll do all the motion. All right? Let's check it with Karini. Karini, you feeling more energy and force? Oh, yeah. It's actually really hard to hold on to right now. And it's true in rope slinkies, it's true in sound, and it's true in light. The smaller a wave is, the more energy is actually in it, as Karini has just told us, right? And right there in the center of the wave, that's called the node of the wave. Hardly moving at all, yet all the energy can still get through. How about a great big round of applause for Karini? We're going to need that.
Let me just say. Now, this is the wave. Remember where he was shaking the wave? Here is a wave that travels, just like a wave in the ocean. And you see as time goes by, it swings positive and negative, and it moves along the direction. Look what happens when it hits the wall. It comes back upside down, and the positive and negative parts interfere with each other. The positives and the negatives can cancel out. That's called interference. That's characteristic of waves. And so you end up getting a standing wave here in black, where you don't see the underlying traveling waves traveling both directions. You only see the sum of the two, which is a standing wave. We're going to do a couple demos of that.
So, one of those waves going across is a traveling wave. And for that, we're going to use this demonstration right here. Our most expensive Rutgers demonstration. A trash can. This trash can has a big rubber sheet on one side, and it has a hole on the other side. More than anything else, this trash can is like a big drum. And what I can do with this trash can, I can hold it like this, okay? And if I hit the bottom, some of you here may actually feel something, okay? I'll do this over here. Okay? Now, did you feel something? Yeah. A little bit? Did you feel something? Yeah? Over there? Yes. Hey, you there in the cheap seats, did you feel anything? No. And if they were to turn around right now and they were to say, hey, I felt something, just believe me. Do you necessarily have to believe them? No, that's not how science is done. You want it replicatable and you actually want to be able to see or get some data out of something. That's what science is really all about. So you really want to see this. And You know, sometimes in science we really can't do that. We actually have to look about how things are doing something by their effect on one thing on another. So Michelle has a candle here, and I can do this with my device. I can blow it out. We do this in astronomy all the time, because we can't go out there and kind of move things around, so we have to see the effect one thing has on another. We do a lot of science that way. But the best kind of science is when you see something. That's what we really, really, really enjoy. So what I'm going to do, I'm going to put some theatrical fog in our garbage can. Now theatrical fog is just glycerin that we heat up, it becomes a fog. They put glycerin in all your food, they just don't tell you, so don't worry about that. I'm not lying about that. So, what you're going to see me do now is happening every single time I hit this garbage can. You just didn't see it. And this to me is one of the reasons why science is so fun, right? Don't you want to build one now? Yeah! Right up the side, not an image, like that. So, this is cool stuff. And I dare you to go home and build one of these yourself. But what's the shape on that front? It's a circle. Thank you, Misha. What's that shape? Wow! So if I take the square and I put it right here on the front of my garbage can, hey scientists, what are we going to see now? How about squircles? Now how about hearts? Rhombus? A square? I see. What are we going to do to find out? Do it, right? That's what the most fun is, doing the experiment. That's what it's really about. So let's put a little more fog in here. Place your bets, win some money from your neighbors. Because it turns out that the only stable shape is the smoke ring. Smoke squares are like unicorns. You want them to be real, but they really don't exist. Sometimes in life and in science, things really do not exist. Okay, we move on. Yeah. There you go.
Now, one thing I want to do a simulation up here, and don't want to spend too much time on a simulation, instead it's so much more fun, is that when you have waves, there's two characteristics of a wave. One is how fast it vibrates up and down. That's called the frequency. And the other is the wavelength, the repeat distance in space, maximum to maximum. Here you see it has a short wavelength and a high frequency. Okay, it's vibrating very rapidly. This one down here has a very low frequency, and it has a long wavelength. Okay, so keep those things in mind. And here we have an object in which we're going to do this one.
Oh, the rope, yes.
Yeah. We're going to set up a standing wave. When you confine a wave, you have to put it together in chunks of half a wavelength so that zeros come back to zero. So the standing waves you're going to see are this one, and this one. We increase the frequency and the number of bumps of the rope go up. Okay, go ahead, Dave.
All right, it's okay, man. It's okay. I can get away with it. So, we have this rope across here, and as Mark showed you before, a lot of it's about a pulse. So if I put a pulse in here, the pulse goes from one side to the other side of the rope. But if I do that over and over again, pulse it in a constant way, you build yourself a standing wave. Let's go back to the beginning. There he is. So that's the pulses going back and forth, but collectively now, and giving us that beautiful standing wave. It's a nice large one. You can see I'm not even running the drill that fast. But if I give the drill a little more energy now, remember, more energy, smaller wave, goes right into the second one. That's the next stage. So now we have the two waves with a node in the middle. Mark can actually show you. You can actually put your hands on the node. The energy will still come through. I can now turn it up even more. Now we got the three. It's right there, but what does Kirk say to Scotty in Star Trek? More power. More energy. More weight.
You want to do the singing rock?
Oh, sure.
The next one David's going to do is he sets up standing waves in a rod, and you will hear the higher frequencies of the different standing waves, and here are the various standing waves that he's got set up. So you can look at this picture and listen to what he has to say.
It's springtime. Have you noticed how warm it is? Yes. Have you noticed Rutgers doesn't have any air conditioning? So, basically, what we have here is that rod. And you know what? In springtime, I spend an awful lot of my life, and maybe you do too, in Home Depot. I don't know, going there for plants, going there for lots of stuff, right? Go there for ground cover. But next time you go to Home Depot, what you want to do is look for the section of the store that sells these rods. Just an aluminum rod. It's right there. Then before you can go to the store, get yourself a little violin rosin, just the sticky stuff they put on the boat, okay? And just get enough to cover your fingers like that. Then you go into the store and you basically grab that rod, hold it right in the center like I am now, and take the violin rosin on your other fingers, and you stroke the rod. And you make the rod sing, but the best part of this is everybody else in the store. What are you doing? What does that sound? Well, it's just me putting my energy into this aluminum rod, and it makes it sing. And notice this. The sound goes away when I put my hand over here. That's because, as Mark can show you, that's the node of the wave that I'm creating with putting my energy into the rod. So if I hold it in the center, that's just fine. Now, I can also show you that we can amplify the sound with a cup. That's why speakers are shaped in this fashion. They're actually a very efficient way of getting sound energy into the air. They look just like cups, pretty, but that's what's going on right there. But it adds that amplification of the end of this rod actually moving quite a lot. Now if I take my fingers and I bring it way up here, this red mark, what's going to happen to the sound, everyone? 4 things could happen. We could have no sound. We could have a higher sound. We could have a lower sound. We could have the same sound. Scientists? Lower, right? So let's take a look. Because it's actually higher. And it's higher because we now have 2 nodes in the rod. And 2 nodes in this rod means it's actually a smaller wavelength than before. Okay? So that's what we have in here. That's what we have in the singing rod. Anything more you want to talk about?
Oh, when you go up to higher frequencies, it just hurts your ears.
Yeah. And that's actually true.
Okay, which one are we on now? We're on the,
Yes, we are. So now I'm going to ask everybody here a very, very, very strange question. Come on in, come on in. Please, come on in. Hey, join us. All right. How big is that sound? How big? How big? Why is that a weird question? You don't see it. How do you know a mouse is really small? You see it. How do you know an elephant in the zoo is really big? You see it. Can you see this? No. So you really don't know the size of this. But you know, here in our show, we're really going to show you exactly how large that sound is. And how am I going to do that? Well, you know the answer to that. Dave's going to use fire. And then he's going to turn that down to a nice, even flame across the top of it. And now what I'm going to do is put that sound back inside. Because when I do that, we see the size of the sound. Down enough. It's got to equalize a little bit, but there it is. That's the sound wave. That's the sound wave that's right now traveling through your ears through the air. If you could see it move through the air, that's what you'd be looking at. That beautiful, pretty sound. do we do to find out? Yeah, you gotta try it, right? So let's go higher. You notice that's higher? And you notice, yeah, let's bring that down. And there it is. That's smaller yet. Now, what else can I do? Well, I can go lower. Yeah, that's fun, right? And now it's easy. So now you see the size of the sound. I hope you enjoyed that. It really is one of my favorite demonstrations.
Well, it turns out that the sound, the wavelength of the sound is different. When you talk, you make a tone with your vocal cords, and you make your ear vibrate, depending on what kind of area, the density of air you've got to destroy this time, you get different frequencies. And so they were.
I'm right here.
Okay. This is helium, much lower density. Okay?
Lower.
Much lower
Much
density.
lower density.
Yeah, much lower density. At my age, you guys never know.
Don't find
It's
it.
one or the other. Okay, it's very low density. I know what it does to me. So let me talk to it.
I don't sound like Mickey Mouse.
It always makes me do this one.
It's true. So I have a gas in this black balloon here. It's actually a higher density gas. So what should happen to mine? What do we do to find out? Do it.
That's right. I have this great radio voice now. I can be an influencer. You'll see me on TikTok, don't worry. The hard part about this demonstration is, unlike Mark's helium that wants to leave his lungs, this stuff doesn't.
So actually I'm going to have to push on my lungs to make it leave so I can then breathe again and not die right here.
Oh, Dave's gonna let me do this one now, so you know either. I look like a fool or it's dangerous. It's dangerous. You gotta come out the way.
Oh yeah.
Don't have to right away. There you go. Okay, we've got lots of professors, but we've only got one day, so I do this. This one floats. Any idea what it is? Yeah, that's right. It floats very nicely. And there'll be a bit of a pop here.
That's a good one.
This one floats too. Turns out this one floats a hell of a lot better.
It's actually a lot cheaper too.
Yeah, it's a lot cheaper. You know what's in it? Hydrogen, yeah. You know anything else about hydrogen? It explodes. When you explode, when you heat it up, it forms H2O, water, and a lot of extra energy.
If you want to use your phone on camera on something, this would be the thing to use it on.
Yeah, and be prepared for a large flash and explosion. I used to do those demos with balloons.
drum like this. The air outside of it is pushing down on the drum like this. But what would happen if I then took all the air out of this drum? There'd be nothing pushing back, right? So what should happen to the drum? It should crush, and you know what? We're going to try it. We're going to pull all the air out of this really large drum. Now, that's not it. Sooner or later, that's not it. Sooner or later, it's going to crush. We don't know how loud, we don't know how violent, we don't even know when. So don't worry about it.
We know it's gonna be a boom. Okay? Now, while that's going, just don't think about that. Okay? I'm going to explain to you. Here we have.
Should be right in the
Here we have, this is a sticker. If you've got one thing to remember from this lecture, I want you to remember this. If you can remember anything after I goes off. This is what happens with gas. You see how the molecules are moving around really fast here? What are they doing over here? Whoa! This is high temperature. This is low temperature. And that's all temperature is when it comes to gas anyway. Fast motion, average motion, lots of kinetic energy, high temperature. Slow motion, low temperature.
Anybody need new underwear? Besides Mark.
It was coming. Now, I just told you about temperature, and you just learned something about pressure. Difference, there was a high pressure, atmospheric pressure on the outside, no molecules hitting on the inside, low pressure. So here you see when the molecules are hitting the wall, pushing on the wall, you have high pressure, but when they sort of just bump against the wall very faintly, then they have low pressure. So pressure also goes with the average motion of the particle, the gas.
That's right. And you notice this is now crushed. If I kept that pump running, it would pull out more of those molecules. The thing would even get smaller and smaller and smaller. What happens now when I pull this hose out? Will it re-expand? No, just like that beer can I crushed on my head last night. That's not going to happen either, but you can hear all the air now re-enter this drum. So you can see just how much. It takes about half the atmosphere to get out of here before we'll actually crush it in that final fan. So there you go, crushing a drum. With our capacitors. Now we're going to move some air.
Just go ahead now.
We're going to move some air, because that's just static air. So if I have here an air blower, I want to prove to you this is blowing the air up. I don't want you to just believe me, so that's kind of going in that airflow. You see it's pulling it right up. And now what I can do is I can take a beach ball, put it right in the airflow like that. And you notice this, the beach ball stays right inside that airflow. It's very stable in the airflow. I can actually take my hand and push on the beach ball. It doesn't even want to fall out of the airflow. But when I take this and move it, it actually follows the air, staying inside the whole time. It doesn't want to leave it like it's on a string. When I move this air source back, it comes right back towards me like that. And when I turn the air off, it's going to go right down to where that nozzle was, just like that. And we know this because it's not just pushing the ball up. That's not what's happening here. The air on the bottom pushing it up, that's not it. That's actually very unstable and would fall off immediately. It's more that the air is going around that ball. By going around it, as Mark has right here, that actually allows us to be very stable in that space. If I can push on it, move it around, it still wants to be right there. Now this is one of the reasons why planes fly in air and are very stable. One of them, it's not the only reason. At the same time, there's a whole lot of things going on those wings and on the plane, including friction. And we can use that friction to move something else.
It's a Bernoulli effect that says basically that fast-moving air has low pressure, and slow-moving air has high pressure. And I keep forgetting what I've done with my laser. It goes back in this pocket here. And so when the air runs around on one side, it has a low pressure. When it runs around, the air scoops past one side, it has low pressure, and the air at rest on the other side is high pressure. It always gets pushed back in. Okay.
So we're talking a little bit about temperature. You know, the molecules are moving really fast in this room, aren't they? It's a warm room. So we're going to bring this on out. And notice, don't be scared because Mark is behind this guy. I'm just trying to keep some distance between you and him.
Yes, they have me do the dangerous ones. By the way, I started off being a low temperature physicist in 1969. Yeah, about 1969. So I've been in this business for a long time. So whenever you handle low temperature things, you should be suited up and have protective things and all that sort of stuff. I know the parameters fairly well, so I'm playing a little looser here. But don't any of you ever do that, okay? This stuff can burn you and do all kinds of awful things, but I'm okay. I'm also pretty old. Here is a flour, nice and soft. And if we put it in liquid nitrogen, it should become extremely brittle. Let me see if I cook for long enough. Actually, low temperature embrittlement is quite typical. Let's see if this will do it. So much for soft flour. Now this one I always like. Let's see, what have I got in here?
You have hot dog, you have broccoli, you have banana.
There's some broccoli.
Mark doesn't like broccoli.
Why do you used to like broccoli? But if you cook it with garlic, it's delicious. When I make it with garlic, I love it. Here's a banana. So that's a banana, right? Banana split, right? And here this just illustrates why you don't want to hang around liquid nitrogen too much. Here's a hot dog.
That's what would happen.
Now this particular demonstration I'm trying to do for you right now is the meatiest one I've got. It has to do with fast-moving air being high temperature and slow-moving air being low temperature. This particular guy is filled with helium, so I let go of it and he go up to the ceiling. But if I put in liquid nitrogen, he won't be condensed, because that would require 4.2 degrees Kelvin, say 77 degrees Kelvin. But if I keep rotating him in here, and he cools off, the air should hit the walls less hard, the pressure should drop, and the volume should go down, and therefore the density of, I think you got too much in here, the density should go up. And eventually the density should go up to a point that will be more dense than air, and this helium balloon won't float anymore. And then when it warms up again, it should float again. So let's give it a while there. The molecules are speeding up. This is exactly what I just showed you. Fast moving. There we go. But if you fuck it up, there's nowhere to go, so the pressure builds up. My father used to work at a nitroglycerin factory here in New Jersey. A famous one near Morristown. Famous for blowing up a number of times. And so here we go constraining it, and then it fails. Explodes out of the wall. When my father got the job at this Morristown, I think it was the Potter Company, William, at any rate. He got the job there. He was a chemist. They took him in the lab, and he looked around. And he said, 3 strong brick walls and then 1 wooden wall. And he said, what's that? They said, that's a blow-up wall. So if you make a mistake, it blows out the wall. They hire a new guy, and then build back the wall. Okay? In fact, if you're going to work with explosives, you want to be out in the open, or you want to have a blowout wall. You don't want the pressure surge of the explosion to stay in the room with you. Okay, so, but it was real stuff. It reminds me of my father. Okay. Now we are on.
Right on this one?
We're going to do that one?
Yeah.
Because we have to turn the lights down.
Yeah. The constant on green is right there.
Oh, we go, you don't think?
Mine has not happened.
No problem? Well, maybe you can figure it out. Okay. Can you,
Yeah, like that.
wait a second, I can put this on, I've got a, wait a second.
There you go.
Okay, this is a block of fluorescent plastic, and the thing we want to show you is how the light reflects off the top surface. And can you see how it bends when it hits the, can you put it right there? Yeah. Can you see how it bends when it hits the surface? That's because the speed of light is less in the block. By the way, I got this block by dumpster diving. There were the particle physics people had it in the dumpster, and I drove in after it, retrieved it. If I put it down here, you see that it will hit the roof, and I have to find the button here. There we go. And it doesn't come out at all. Can you see that, how it stays inside? That's called total internal reflection. And that happens someplace else. Do you know where it happens? In your house? All the time? Fiber optics, yes. That's right. That's what you use to contain the information on the light cables that bring in your cell phone and your internet. This is a fluorescent material. Oh yeah, I have to turn this guy on. Right. And you see it glows nicely. That's what they like because charged particles go through here and make it glow. And here's a rock that I also dumpster dove for. You can see it has a ribbon of fluorescent material in it. Franklin, by the way, the Franklin mine in northern New Jersey is the world center of fluorescent minerals. And the Rutgers Geology Museum has a good display also. And the mine tour up there in Franklin is wonderful also. Now, typically the students prefer something that embarrasses the professor. So I do this. I used to have fluorescent underwear, but I stopped doing that. Okay, yes, that looks for the ultraviolet. Oh yeah, here's the that's green. Where's the violet?
He's there.
By the way, you have to be careful how you. There's the violet, and now. Not a very good artist.
You can basically make pictures with light. It's phosphorescent sheet that absorbs the energy, but it's a purple laser. But what color comes back to you? Green. Green. We're actually doing modern physics with this because it's changing its state.
Wait 1 second. Here's a very bright green laser, and it does nothing.
Right.
It doesn't have the energy to kick the electrons out of the molecule. The violet has more energy to kick the electrons.
That purple wave is a lot smaller. That UV wave is a lot smaller. What does it have? More energy, as we said before. So there you go. No, we're going to do your glasses. We get to do the glasses.
Oh yeah, well that's
So does everybody have a pair of those glasses?
Oh, wait.
Raise your hand if you don't have a pair of glasses.
I forgot the one other thing they're going to fluorescent toilets.
Can everybody see that bright light bulb right there in the center with your glasses on? What do you see on one side and what do you see on the other side? Rainbows. Who doesn't like a good rainbow? And what we get from those glasses, the diffraction ratings. They're used every day in science. They are our gift to you. Rutgers is actually giving you something besides a bill. So, you can now see that rainbow due to the temperature of that light bulb. We know from the rainbow you see that that light bulb, that filament inside the light bulb is actually 3,000 degrees. We know that because of the rainbow you see. We know the temperature of any star in the universe using the same method. We know the temperature of the surface of that star due to the rainbow we see from that star. Using those glasses like you have on your face right now. They're very, very powerful tools. In fact, if I take this light bulb and I turn it down now, you'll notice that we're changing that rainbow on your glasses. What colors are starting to disappear? That's right. We're actually having them leave it right now, so we have them leaving it. We bring it way down to here. This is now 1,000 degrees, okay? But you can see how much the color has changed. You see Betelgeuse in the sky. We know the temperature of that, but it's a big red star. It's a lot less hot than those other bright blue stars. Mark's going to talk about that in a second. I bring it way back up, and all of it reappears. Now what I'm going to do is turn the top one on. Please compare those two rainbows. What's the top one missing? Yellow. There's a black line where the yellow should be. I don't say it. Bulb manufacturers think that people don't like that yellow light mixed with their light. So they coat the interior of that bulb with a material that absorbs the yellow before it reaches you. They're stealing part of your light. How do you like that? So this is exactly what astronomers do. They look at any star in our universe. If there's lines like that in the starlight, they know exactly the material that's in between us and that star from anywhere in the universe. You're doing it right now. I turn that one off. I turn that one off. And now let's look at some sources, because this right here is that most famous element, the one we just blew up. If you look at that through your glasses, you're going to know that you have just a few simple lines. Okay, you see those lines? Right. Mark, you want to talk about those lines right now?
Sure, that's hydrogen. You see the red line? That's the most famous line in the universe, the red Balmer line. That's a transition between two levels in hydrogen. Every time you see that, you know you've got hydrogen somewhere.
So we got another source right here. I turn this one on. What is that one?
Is there a yellow line in it? That's helium.
This was first seen on the sun. It's actually named after the sun. We didn't even know about helium until we kind of like saw it on the sun. We would look for it here on Earth. But that's actually helium. Those are the lines that you use. Those are fairly common too in our universe. Not like some of these. I'll turn that one off. I'll turn this one on. You see those blue lines. Some green. Bring that way over there. Well, this actually is mercury. And what I have here is a mercury bulb over the top. If I turn that bulb on, you notice how the colors from that bulb actually are very similar to the colors of that mercury source. That's because there's actually mercury in those old style Ceothal bulbs. That's why you don't want to go too near them when they break. That's a hot mercury. Now if I turn this one off, and this one off, I can turn our last one off. That's this one right here. And this one has a whole lot of nice lines, but it's also very, very pretty. This is neon, the same as you would have in a neon sign. But please, take those glasses home. Use them around your house. Use them to see all the lights in your house. Kind of compare what those lights are giving you through the glasses. Go ahead and look at holiday lights. Go ahead and look at street lights at night. I know, they think you're crazy, but that's okay. Go ahead and look at a full moon. That's one of my favorite things to do with these glasses. Just never, ever, ever look at the sun with your bare eyes or with those glasses on. That's not a good thing to do.
It can blind you. Okay, so you you don't even try it once. Okay, don't ever look at the sun.
But let me show you how much fun you can have with these. I turn this one on, and notice what happens as these LED lights actually start to shift color. You're actually seeing color mixing in action. The side rainbows are actually showing what the center colors are made from just with your glasses on. So you can be quite the scientist with this. And if you have to do a science fair sometime in the future, hold on to those glasses because you can use them in your science fair. So there you go.
If you have sunlight coming into your house, you can put the diffraction rate into the sunlight and you'll see a rainbow. That's the way you can see the sun effect. Here, by the way, and here's hot white stars that are very high temperatures, Rigel. And then, of course, the brightest star in the sky is Sirius. And right here, there's a glowing cloud of hydrogen gas. It's just like the one we have here. This is not its spectrum, but this is what the spectrum would look like if you honed in on the Orion Nebula, because it is just glowing hydrogen gas. Okay. And there is one other thing I have here. Yes. The helium that you saw was discovered in 1850. They didn't know if helium is an element of the periodic table because it all floats up away from the Earth. It isn't around the surface of the Earth. But they saw it in a spectra of the sun. They saw that yellow line during the total solar eclipse, and that's how they found helium. Named it after the sun that they found it.
Now let's see if we can find all of you with this camera. You see our side screens right here? This is going to be you, our audience. This is a FLIR camera. It basically shows what you look like in infrared. And you're all very, very warm. We have one hot audience. That's right. But this is you, and you're always, always, always putting out this wavelength. Always. Right? You're always glowing like you just don't know it because you can't see an infrared. Okay? Now infrared is right next to red. It's right next to it, but it doesn't work the same as visible light. How can we show you that? Well, Mark here has a sign. Can you see Mark through that sign? Mark, turn to them. Can you see Mark? Visible light goes right through it. But if I take this camera and put it on Mark, and then he puts that sign in front of his face, we can no longer see Mark. Infrared light does not go through glass or plexiglass. Visible light does, but you knew that. You go to the beach, you park your car, you go off to the water, you come back 5 or 6 hours later. How hot is your car? Hot. That's because the energy of the sun comes in, tries to leave as infrared light, can't get out of the glass. That's why your car gets to quickly to 200 degrees without really over an hour. It would be very, very hot. Danger zone. So Mark has a whole other object. What is it? A black plastic trash bag?
Yes.
We're going to put a professor inside a black plastic trash bag. Notice you can't see Mark.
Dave,
When you turn the camera on, you can now see Mark. He's sticking his tongue out at you. Infrared light doesn't work the same as visible light. We just want you to know that. Okay? Big round of applause for Mark. Oh, you don't want to know. You don't want to know. But before you, I want to tell you.
Oh, wait.
Okay, now, the fall part lectures we do, we always call the Faraday lectures because he gave shows for the general public and for children. And this has to do with the Faraday effect we're talking about now. And I guess the first thing I should do is solve this. I don't see it. Here I have a magnetic field. And now, what happens is that the Faraday effect is that when an object hits a magnetic field, it induces electrical currents. And that's a way of dissipating energy. So if I roll this thing down an inclined plane, when it hits the magnet, it hits a magnetic field. Changing magnetic field creates a current. When it comes out the other side, it continues on. And if you're real careful, you can see when it's exactly in the middle, it's neither in nor out, and it speeds up. So take a look. Like butter. And then it does that little speed up when the magnetic field isn't changing. Okay, so it's a changing magnetic field that induces currents. And I want to try and prove it's a changing magnetic field that induces currents. Because here I have an object that has a lot of it removed, but it still has a continuous current ring. So electrical currents can flow in a circle. And so you see the same effect, even though most of it is missing. Changing magnetic field induces electrical currents. Now this one is chopped fiendishly from one side and then the other in a zigzag pattern. So there's no contiguous circular path. So when it hits the magnetic field, the Faraday effect can't take effect and it goes through. Now, I've got a couple others here. Here, if you pull it, things are impeded from flowing. The resistance of the material increases due to the fact that the atoms are vibrating, the electrons are getting bounced off and backwards. And so it's higher resistance and higher temperature. So if you cool it down, you get this effect, just like the nitrogen temperature on steroids.
Oh, that's pretty good. Wow, you really slowed it.
Well, it slows down long enough to freeze. Okay.
Now think about it. If that was a piece of steel that Mark was riding down there on through the magnet, what would happen to the piece of steel? It would stay there, right? It would hold right out to that magnet, right? And what I have here is a magnet that can move. Mark was actually moving these materials through the magnetic field, but here my magnet can move. And right here is a large piece of copper. Now is copper magnetic? No, and if I put this right here on here, it doesn't really attach. But if I take the same piece and I drop it through this tube, you'll notice there's quite the effect on that magnet. What we're getting now is that slowdown, the same as you saw through there, only now the magnet is slowing down, not the material. So that's why this works. You have the flux lines coming from that magnetic field, interfacing with the copper tube, which creates a corresponding magnetic field which slows it down. The secret to our world. This is why Tesla was able to do so much.
The original one.
The original one. There it is.
Okay. You ready for the next one?
Yeah, that's for you.
Okay. Here, we physically were moving things in magnetic fields to get the changing magnetic field. You can also get a changing magnetic field by just hooking up to the line current, because the electricity, well, not quite. The electricity runs in one direction, and it flips the other direction every 60 times a second. Okay? And I'm holding my hand like this. This is the right-hand wall. When electricity goes around in this direction, it creates a magnetic field in the direction of my thumb. And when it goes around the other direction, it creates a magnetic field in the other direction. So that means if I put an alternating current in this coil, I've got a changing magnetic field here all the time. Changing magnetic fields will induce currents, and when you get those induced currents, you'll pick up the induced currents in here, and they'll be like two magnets repelling each other. And so that's why we call this the ring plane. And I used to call children up here, and I'd turn it on and say, put it on. Actually, I'd say, put it on like this, and then I'd turn it on, give it to them, and they'd go on like this. And then I'd take it from them, turn it off, and say, no, put it on like this. They've advised I shouldn't do that anymore. But then I would show them this one is a contiguous, but it has a slice in, so no electrical currents in the circle, and no induced currents. Of course, they don't trust me at that point, so I have to show them really turning it on. And the last step is you want to show there's really electricity moving in a circle, and to do that, you do a thing called a transformer. You put a pickup coil here so that the induced currents pass through this light bulb, and the changing magnetic field produces an AC current, and through space they couple each other by changing magnetic fields.
Notice again, no physical contact, right? Just that flux from the wires is actually what's causing the bulb to light, and that's what we use in our world.
And as usual, if you cool it down, you get the effect on steroids.
We have one last group of demos to do for you, and for that I need 2 volunteers. Once again, nobody wants to volunteer. What's wrong with you people? Come on now. Come on now. What's your name? Thank you so much for joining us. We're really happy you wanted to join us. Come on over here. Okay, what is your name? Naya, that's an excellent name. So good to meet you. My name's Dave. You two, do you know what you actually volunteered for? The bed of nails. Did you change your mind? I actually would. But don't you worry, you're not getting anywhere near the nails. It's actually my job to get near the nails, or maybe Mark's job. We're going to find out. So what we're going to do is we're going to take this bed of nails. We're going to put it right down here on our floor. Just like this. We have a second bed of nails. And we're going to let Mark lie down on this one. And we're going to take the second one, we're going to put it right down, nails down on Mark. And then you two get to stand on Mark. What do you think, John? Do that? All right, you got it. Thank you so much. Yeah. Come on, Mark.
Come on, say you gotta get this.
These are, by the way, very real nails. I made these things myself, so I know. Bed of nails now on top of Mark. Put your hands. And he is now a bed of nail sandwich. Basically a bologna sandwich, but that's a whole different story. Come on over here.
No jumping.
No jumping. Right on those feet. That's it. Mark now has 2 human beings on him. Hey, Mark, how you doing? He says thumbs up. You can step on down. Just step on down. Fantastic. Well, then a big round of applause for that. All right. So, that looked just like a magic trick, didn't it? But remember, it's not magic, it's physics. We want you to understand this. You stay right there. Here I have something remarkably similar to Mark. Thin-skinned and filled with hot air. And here's a big bed of nails. Here's a not-so-big bed of nails. And here's a really not-so-big one. But think about it this way. I weigh 200 pounds. That's what I weighed when I weighed myself this morning. If I was to take a bed of nails with one nail, and take my body and lay across this one nail, how many pounds of force on that one nail? 200, more than enough to drive that nail right through my body and kill me. Let's say I had 10 nails in my bed of nails. How much force on each nail? 20 pounds, more than enough to drive those nails right through my body and kill me. Let's say I had 100 nails. How many pounds of force on each nail? 2. And 2 pounds of force on a nail really does hurt. It does. But it won't go through your skin. You need 16 pounds of force on a nail to go through human skin. I know. I'm a scientist. I did the experiment. Well, I did the experiment. So if we think of this as Mark, will Mark break on that bed of nails with all those nails? What do we do to find out? Do the experiment. That's what it's really all about in life. I think it's not just science. It's actually everything. Do the experiment. So you can see it's not breaking. There's not enough force in any one nail to go through the skin of the balloon. How about here? Maybe. You put maybe on tests? You can't be kidding me. I want to be your teacher. How about now? What do we do to find out? And you can see no. How about here? Yeah. It's also our last one, so that means yeah. Yes. Then we'll break. Now, here that we want you to really understand and see. So what I got here is our sign. This is what we used in the city when we ran our show in the city. It was a lot of fun to do. One of my rocking chair moments. When I'm in a rock chair, I'll be like, yeah, I did that. But it looks just like a guillotine. We're actually going to put this right here on Mark's neck, just like this. Oh, you stay, yeah, you're not done. Now, when I first got to Rutgers, Mark was one of my professors. Yeah. And he gave me a lousy grade. So what I have right here is a big cinder block. And we're going to put it right here on Mark's rock hard abs. Let's have some jiggle a little bit. And here's the third part of our experiment, sledgehammer. Does Mark live? They say no.